Hello, it's Keith here, and this is lesson 5 of the platform-specific series of my PDP-11 programming tutorials. We're looking at the UKNC again today, and we're going to be learning how to create a bitmap font on this system. Now, the UKNC is a particularly weird system because it uses multiple bit planes like a lot do. It uses a subprocessor like a lot of systems do. However, it allows us to map the different bit planes to different memory that is accessible by the two CPUs. Now, last time in lesson 4, we used a scanline table that allocated 2 of the bit planes to our main CPU, which is the CPU running our code, and the remaining 1 bit plane to the sub CPU, which runs the peripherals. The reason we did that is it's not possible to map all 3 to the main CPU or all 3 to the sub CPU. So we've now got these bit planes in different places, and what I wanted to do today was create a bitmap font drawing routine which would show our font to the screen without using the firmware in any way, and this is going to do this from both CPUs. The reason we're doing this is this allows us an easy way of testing. We can get our output, our hexadecimal output or whatever we need, to the screen from either CPU without the firmware necessarily working. So we can do things like disable interrupts, mess with the memory, corrupt the operating system, and still get our results to the screen. So this is really something to build on in future examples. So what we're going to do today is we're going to create 2 versions of a character drawing routine which will show a character to the screen using our Chibi Akuma's bitmap font, which is the common font I use in all of my tutorials. You can see it here in Aku Sprite Editor, which is my sprite editing tool I wrote. So we're using this font today, and you can see here we've got 2 examples. Now, this more complex Hello World example here is shown from the main CPU using 2-bit planes. This second example here is done with the sub CPU, and we're just showing a few characters to the screen. So we've got these 2 print character routines, and we can then build on those to do things like print strings or even dump our registers to the screen once we've got the basics of getting a character to the screen. So that's what we're going to look at today. What we're not going to look at today is how to set up the scanline table. Please see the previous example for that, lesson 4. We're also not going to discuss the code that transfers the data to the sub CPU and runs it. Again, we've covered that in previous lessons. So please take a look at that there because it's too complex to discuss today. Okay, so our font. Well, our font is this one here. This is a black and white font, and we're outputting it in a 1-bit per pixel format. There is, however, a quirk for the UKNC. Now, normally the bits would go from 7 to 0, and that would be the pixels from left to right on the screen. However, they're reversed, it seems, on the UKNC. So the leftmost bit, bit 7, is actually the rightmost pixel on the screen in the bit plane. So I've actually created a new output option here in the UKNC menu here, and we've got save raw 8x8 1-bit plane. Now this is outputting our font in the correct right to left format for this example. Usually I would use the exact same bitmap file in every example and I would convert it. However, it seemed a bit crazy to bit shift all of the bits into the correct positions in memory. That would seem quite wasteful and not really any benefit to it other than bragging rights of claiming I'd use the same file in every example. So we're not going to do that. Okay, so let's get our example out of the way here and let's go over to our source code and let's take a look. Okay, so we've got our code here. This is the start of our code, and we're using this send command here to transfer a program to the sub CPU and run it. But that's just the initialization here of setting up the bit planes. As I say, we've got 2 bit planes to our main CPU, and then we've got 1 bit plane to our sub CPU. Now, when we want to draw to our main CPU, we're using this print string routine here. I think we've used this before. Basically, it prints a character 255 terminated string. I always use character 255 termination in my tutorials. That's the way it is. So we're just doing that here, and we are running this print character routine as a subroutine for each of our characters. And what I've done today is I've written a new print character subroutine that is 100% compatible with the old one. So things like the monitor function, which worked before, still work just fine. And here is our print character routine. So we're backing up all the registers, we're changing so that when things return, they're the same as they started, and that's how we can make something that's nice and easily compatible. Now, our font uses 8 lines per character, and each line is a single byte. So each character is using 8 bytes, and you'll notice that the first character is the character space, which is character 32. Now, what we're doing here is we're shifting the character number to the left 3 times, effectively multiplying the character number by 8. We're then adding the memory address of our font. Now our font, where is it? Here it is, here's our font. And here are the characters, and you can see that first one is space here. So we've put that in as text there. We've converted that and put that in as text. Now Acrosprite Editor, I think it outputs a binary file, and I've got a program that converts binary files to text that I use. If we just drag our font onto this program here, this program will output text data that relates to the binary file, and then we just need to change the settings here as required. So in this case I'm using octal, and then if we just do redo here, you can see we can convert our data and just set the prefixes and things as required. That's how I've created the text data for the font file today. Now the font file doesn't have any characters below space, so we've subtracted 32 times 8 because we are skipping the first 32 characters here. And because we're in octal, that's in 400 in octal there, so we're subtracting that there, and that is calculating the correct memory address in the font file, in the font data, for the character we want to show. Then what we're doing is we're calculating the VRAM destination based on a cursor X and a cursor Y position, and we have 2 bytes of data for our X and Y position. We're starting 10 lines down. So each line of our screen is 40 characters across. Each of these characters uses 2 bytes because we're using 2 bitplanes, so that's times 2. And there's 8 lines per character, so that's times 8. And this gives us 640 in decimal or 1200 in octal. And so what we're doing here is we're multiplying the Y position by 1200 in octal. And that is calculating the VRAM destination of our Y position. We're then adding the VRAM base, which is at 100,000 in octal. That's the start of the screen memory from the CPU side, because remember there's a CPU and there's a PPU, and the CPU and PPU have different memory addresses. So that's where we've mapped our screen memory to. We're then taking the cursor X position and multiplying that by 2, because remember 2 bytes for 2 bit planes per character. And then we're going to start our main loop, and our font is 8 lines tall, and that's 10 in octal. Okay, so what we're going to do here is we're going to move 1 byte from our font to our screen memory here, and so that's what we're doing there. And this is we're going to increment the source, and we are just going to leave the destination unchanged. So we're only actually setting one of the 2-bit planes here. So I guess if we overload some of the data, it would maybe look a bit weird. We could change this and set both of the destination bit planes, but for simplicity here I'm just setting the one. So after we've transferred a single line of our font, we're then moving down 1 line of the screen to transfer the next line. So we're adding 120, which is the amount of bytes in octal of each line of the screen, and then we're just repeating until we've drawn all of the lines. Now once we've drawn a character, we're increasing the cursor X position, and we're comparing our X position to 50 in octal to see if we're at the end of a line. Why 50 in octal? Well, because 50 in octal is 14 decimal, and that's the width of our line in characters, so that's why we're doing that. And then if we are at the end of the line, we're just running this new line routine, and all that does is it clears the X position and increments the Y position, and that's just because our monitor required that functionality. So that's how we're setting a character from the CPU side, which has access to the 2-bit planes. Now the function for the sub-CPU version is almost the same. There's a few differences. Now this is relocatable code, so this means that we don't know the exact memory address that this is going to run from. So when we use something like the font data, we're calculating the offset to it by using the current program counter address and adding the offset in the source code to the current program counter, and that will calculate the relative address for the new position of the font in the sub-CPU's memory, because we're transferring the font across to the sub-CPU with this program code. Now the VRAM base is different. It's at 40,000 on the sub-CPU's memory, so that's our base there. And we are doing the same kind of thing with our X and our Y position. So our X position we're loading in here. Now we're just adding that straight to the VRAM base here, because we don't need to multiply by 2 anymore. We're just using 1 byte, 1-bit plane this time, so we don't multiply the X position by 2, we just add it straight away. And instead of 1200, we're adding 500 in octal this time and multiplying that by the Y position. That's because each line is now only 40 bytes, not 80, because it's only 1-bit plane, so that's why we're doing a different multiplication there. The transfer routine is basically the same. Again, the amount we add after each line is lower now, and at the end we've got the same thing. We've got a different new line routine. All of these routines have had to be replaced because they're running on the sub-CPU, so they have to cope with the relative addresses, but apart from that it's basically the same. Now in this example I've just printed a few characters to the screen. I haven't done a show string routine because I didn't need it for today's example. It was just a basic example of how to get characters to the screen from either CPU. So we can use these later on in our testing, and if we're in a situation where the main CPU is unavailable to us, maybe we've crashed it, or maybe we just can't get the data we want to the screen from it, so we need to do it all from the sub CPU. We now have some test routines we can do that with. Now we're going to come back next time. We're going to be looking at the UKNC some more, and we're going to be looking at reading in the keyboard directly from the sub CPU. This is why I wanted these routines. I wanted to be able to do things entirely on our own without having to worry about the firmware and without having the limitation of worrying about which CPU was available to me, because to read the keyboard we need to use the sub CPU. So if that sounds interesting to you, please make sure you subscribe and make sure you like the video as well. That would help me out. If you want to see more of this kind of thing, it would help me out if you backed me on Patreon. I have a Patreon account for people who like my videos, and they support me, and they support me researching weird things like the UKNC and PDP-11, because they're not things that I'm going to use in my daily job very much, are they? Anyway, hope you've enjoyed this today. Thanks for watching, and goodbye.